pattern. So with the tetrahedral pattern, as you see, the ligands are approaching from the off axis. So when you have your XYZs, notice that this is not coming in at the XYZ direction, and that's how you're creating a tetrahedral pattern. So the off-axis orbitals experience a higher repulsion compared to an on-axis set, which is x squared minus y squared and z squared. So the splitting reverses compared to the octahedral. So that's it. That's the, if you know your octahedral splitting pattern and the orbital designation, you should know that the tetrahedral is exactly the opposite because the orbitals approach from the off-axis direction. Okay. Now we have another splitting pattern. This one you don't have to memorize. If you have to work with it, I'll provide you with the pattern. But this is for square planar, because when you have 4 ligands, if you have a situation of ML4, it's either tetrahedral or square planar. With the square planar, and you want to pay attention to the problem, because the problem will tell you what type of if it's tetrahedral or square planar, the problem will tell you. If it's an octahedral complex, you already know the splitting pattern. So with the square planar, the orbitals that experience the most repulsion, you can see now the ligands coming in from the x and y direction. The orbitals of the x squared minus y squared, they experience the greatest repulsion. So this is like dx squared minus y squared, which is listed for you over here. So anyway, you just fill your electrons from low to high. And in this one, you just have to, if you have, let's say, 5 electrons, I'm just making up a case here. The way you fill is you put 1 and 1 here, and then come back and fill this set. So it's 4 electrons, and then you put the 5th on top. And then if you have any more, you have to first fill, let's say you have more electrons, fill this one, then come here and fill this one, then come here and fill that. So we go from low to high, but the first orbital sets are at the same degenerate energy level. That's the dxz and dyz. This chapter and coordination compound chemistry has a lot of applications, and these applications run anywhere from purification of metals. We extract metals from ores, which are natural rocks that the metals come in the form of compounds in these rocks. And for example, silver and gold could be separated by creating a cyanide complex of them. Nickel is separated with a carbonyl complex of it. That happens to be a gas, actually. We also use coordination compounds as chelating agents. The complex ions can be a chelating agent because, for example, if there is a situation where there's lead poisoning, you can chelate, which means to combine one ligand in more than one binding location to the metal ion. In this case, we went over the EDTA that has a hexadentate situation. So there's 6 binding positions, and it creates a very strong bond, and it can actually take the lead out of its water. Say if it's complex with water, it can replace the water and take it out, and then bond with the lead. In this way, lead could be separated from say blood. If there is a heavy lead poisoning and there's a lot of lead in the blood, you can go through an EDTA therapy situation, and typically, it removes the lead from the blood level. So patients that go through that therapy, they experience reduction of lead in their blood over time, which is good because we don't want lead in our blood. It causes a lot of issues, including learning disability. The other application is chemical analysis, and you can see that the color of the complexes can be different. So if you form a color by combining a metal ion with a particular ligand and you get a particular color, you can now analyze the level of the compound. And we're going to do that in the lab too. For example, the cobalt thiocyanate complex is blue. In this case, the iron thiocyanate is red. Okay, so there's also a lot of applications in biology. A lot of biological molecules, which we call proteins, have transition metals somewhere in them that creates a very active function of that protein. And for example, chromium, it works with insulin to control utilization of glucose. Manganese is for fat and carbohydrate synthesis. Molybdenum is involved in hemoglobin synthesis. And iron, you probably know that from your biology course, excuse me, that's involved in oxygen transport in a molecule called hemoglobin. Copper is involved in synthesis of hemoglobin. And zinc is a very important metal. It's it participates in the function of more than 70 enzymes. And so you definitely do not want to be zinc deficient. And it carries a lot of, these enzymes carry a lot of biological functions. So when we talk about the biological applications, this is a ring that's called a porphyrin ring. A porphyrin ring is this structure right here, and wherever you have these bends, you have carbons, and the hydrogens are not shown to you. There are hydrogens to have a balance of octet on carbon. And the center of the ring is very important because it creates a very specific space for the metal ion to bind here. And so the metal ion can bind with these nitrogens because they all have a lone pair of electron on them. And it's sort of, the porphyrin ring immobilizes the metal ion within the structure of the protein. And amino acids, actually there are amino acids all around this typically too. So please know that there are 4 nitrogens that bind with the metal ion in the center ring, which is called the porphyrin ring. So these are some important biological molecules that they use metal ions in a complex way. Hemoglobin has 4 parts to it. A protein of hemoglobin is like a 4 building block format, and each building block has a porphyrin ring, and in each building block in this porphyrin rings we have an iron. So the iron that we have here is Fe+2 state that is ready to absorb oxygen for us. So this is the top view of the porphyrin ring, and the ring is a little different because it has some extra functionality or functional groups on it, but essentially the ring is the same as before, as the previous diagram that I showed you. And you can see how you can have 4 bonds with the iron. And these bonds are they're not quite in the square planar format because 2 of the nitrogens are tetrahedral format, and then 2 of the nitrogens are trigonal planar. So there's a little offset of angles, but essentially there are 4 bonds here that you see. Now, I brought this new diagram into this slide to show you that the iron in the middle of the porphyrin ring is also held with an amino acid, I think it's called histidine, that holds the iron by having another nitrogen that bonds from the below side. So you can see that the bond is 4 bonds to nitrogen from the porphyrin ring, and then there's another lone pair that binds with the iron from the lower end of the iron. And now there is 1 space that's available here. So this is the space for oxygen to bind. And it actually binds in this location right here. So you can think of it as the last position of the tetrahedral is where you have here. So if I go ahead and show you like where oxygen come in, I'm just going to pick a different color. And so what happens is your oxygen binds right here in this position, like O2. So the binding of oxygen to the iron in the hemoglobin is not very strong. It's actually a very weak bond, and it's what we call reversible bond. Reversible bond is very important for the functioning of hemoglobin, which is oxygen transfer, because if this bond was very strong, then oxygen would not come off of iron, because you really want the oxygen to be released at the environment of the cell, and there is some pH dependency on that as well. Environment of the cell when it needs oxygen is acidic. So when hemoglobin molecules through our blood circulation make it to the vicinities of the cells that need the oxygen, the acidic environment helps the release of oxygen. So oxygen just comes right off. So you don't want the bond to be strong. In fact, molecules that bind strongly with the iron, they create a very deadly effect in our breathing. We can choke to death. One molecule is carbon monoxide, which creates a very strong bond, and for basically for the bonding, like molecular, based on molecular orbital theory, creates a very strong bond to the iron. And so if there is any exposure to carbon monoxide gas, our hemoglobin basically doesn't have any space for oxygen. So essentially, we choke to death. So carbon monoxide is very deadly for that reason. Okay, let's move on to another important biological molecule, which is chlorophyll. Chlorophyll again has the porphyrin ring, and there is magnesium in the site of the nitrogens. Mentioned that our enzymes have certain ions. Zinc is important in functionality of many of the enzymes. For example, this enzyme is called carbonic anhydrase, and it essentially decomposes carbonic acid. This process is slow, and it doesn't happen. We want it to be happening faster. So by putting a catalyst in the presence of a catalyst, and the catalyst is carbonic anhydrase, that's abbreviated as Ca, this process happens much faster. So this is important because we want the carbon dioxide to be released from our blood, and we want to expire it out as gas. So in this case, this is a tetrahedrally complex zinc. So the zinc ion is complex in a tetrahedral format. I told you about this particular, this is a anti-cancer drug. It has anti-tumor properties, and it is called cisplatin. The cisplatin is the cis version where the chlorides are in the next to each other format, and there is an ammonium connected to each of the other sites. It's a square planar complex of platinum. So that's it. I hope you get to study this chapter in detail. There's a lot of good chemistry in this chapter that I want you to really, pick up and pay attention to. And so that's the end of this. So good luck, everyone, and bring your questions to my office hours.